All right, let's take a look at the work problems for chapter 1. So let's go to the next slide. So your work problems are primarily going to come either from Zumdahl's chemistry or from Brown and LeMay's chemistry, with occasional problems from McMurray and Fay. Uh, there won't be very many of those. And then also a lot of the multiple choices I'm taking out of Mr. Mack's AP website. So I recommend, if you have time, first of all, be sure that you go through the problems here in the work problem sets. And then if you've gotten to the point where you feel like you really know these, then if you can, go ahead and go on to Mr. Mack's AP website, and you can access that either by, I think I have the links on the last slide in all of the work problem sets, but also you can just go into Google or whatever and type in Mr. Mack's AP chemistry site, and that Mac is M-A-C, Mac. So a lot of the multiple choice work problems will be taken from that. And then there's a bunch of other ones that you could study in his website. And then next slide, the solutions are provided all by myself. I did all of these problems directly from my own brain. I didn't copy them out of anyone else's textbooks or answers or anything. So if you wanted to, you could also look at the problems as far as like in Mr. Mack's website, if you want to look at the same problems and see what his answers were. But when they're multiple choice, they're probably just going to give the answer, but he may have given some explanation or done some work on it to show you how he got his answer. So if you want to look at those two, you can. Next slide. Okay, so let's go ahead and get started. I went kind of long on the lecture notes for this chapter, so I'd kind of like to abbreviate these work problems as much as I can, just to kind of even it out a little bit so you don't have to spend that much time. So here we are. Number one, this problem says you may have noticed that when water boils, you can see bubbles, and then they want to know what's in the bubbles. And the answer is this. First of all, when you have water, it's going to have air mixed up in it somehow, because water gets air bubbles that they're just so small you can't see them. So what happens is two steps happen when you boil water. First of all, the air that's trapped in the water will start to come to the surface as you get it hotter and hotter. But before the water actually reaches its boiling temperature, the air is going to start to come to the top. And then any air that's in there will leave before it actually starts to boil. And then at about 100 degrees centigrade, depending on your elevation, the water itself will start to boil. And the way that works is that at the surface of the water molecules will get enough energy that they can escape the liquid phase and go into the gas phase. So the answer here is, at the beginning, it's air. And then after that, it's actually water vapor. So let me get my marker working here. So this is what's going to be happening at the beginning, and then water vapor here. You will never have any of these gases like carbon dioxide or hydrogen or oxygen. And then B says, is it a chemical or a physical change? We've already talked about this. It's a physical change. It's a physical change. Okay, next slide. And here's your answer. If you want to take a look at it, you can pause the video. Next slide. A gas at 25 degrees centigrade fills a container whose volume is 1.05 times 10 to the third cc's. The container plus the gas have a mass of 837.6. The container, when empty, is 836.2 grams. What is the density? So we need to remember the formula here for density, and the density formula is that it is the mass over the volume. So mass divided by volume. Do we have the mass? The answer is no. We have the mass of the cylinder when it's got the gas in it here, and then we have the mass empty here. So to get the mass of what we want, which is the gas, we have to subtract 837.6 minus 836.2, which is going to be about 1.4 grams. So then once you do that, you divide by the volume, and we have that. The volume was given to us straight up right here, 1.05 times 10 to the third cc's. So what we have here is a two-step thing. First, we have to subtract 837.6 minus 836.2. And that's an addition subtraction. And this is the way that you do sig fig problems the way Brown and LeMay wants you to do them. It also turns out that when you have a question that's asking you to do a percent error, then it turns out that this way works really well for that too, even though the sig figs don't actually work out the same as they would if you did it one of the other textbooks ways. But I think really for this kind of problem, for this particular problem, or especially if they specifically say in the problem statement that we're looking for sig figs here in this problem. And there's, as I said before, there's always one or two on the final that will say to the correct number of sig figs. So that's your clue. You want to be sure on those at least that you do the sig figs absolutely right. And then also when you have a percent yield problem, it's actually better so to do it this way. So let's look at what's different here. What's different is that what we're going to do when they give us this problem, what we want to do is we want to do the subtraction part here first. We want to take the 837.6 and subtract 836.2. And then we'll follow the rule of addition. Now, it's a kind of a pain because you have to stop here and you say, okay, how many decimal places? But it turns out that in these particular problems that I'm talking about right now, it isn't really going to slow you down that much. So, because if you notice here, these both have one decimal place, so I mean, it's obvious here, the answer for adding and subtracting is going to have one decimal place. But even if it didn't, even if one was one decimal place and the other one was two decimal places, it still really won't take that long. Well, in that case, it would just be the same because it would be only one decimal place. If you had one that had two and one that had three, it might take a little longer, but it's not that big of a deal. So for these kinds of problems, and when I say these kinds of problems, I mean a problem where you've got to subtract something like this first and then divide it by the volume, or a percent error. Let me write that out so you can get a visual picture of this. And if you don't know what I mean by percent error problem, we're going to look at some in a minute, so you'll see it, and I'll try to remember to remind you. Then just use this technique right here, and this is the way the book actually wants you to do it all the time. However, we won't be doing it all the time, but anyway, so I'll try to remember to point out when we get to a percent error problem, or you can just try to remember to watch for it. Do your subtraction first. So one, do your subtraction or your addition, but it usually will be a subtraction. And then secondly, do your division, but only after you have, at least for this kind of problem, done your correct number of sig figs. And I'm going to stop with SUB subtraction. I'm going to stop there because it's just taking too long. So when you subtract 837.6 minus 836.2, you get 1.4 grams. So you want to get that to the correct number of decimals. And it already is. 1.4 already is because it has one decimal. So 837.6 has one decimal. 836.2 has one. The less of those would be 1. So you choose 1. So you want 1 in your answer, right? So, but your answer already has 1. It's 1.4. That's your answer. So you don't have to do anything. So now you do your division by dividing 1.4 grams by 1.05 times 10 to the third centimeters. And I'm getting that from right up here. And when you're dividing or multiplying, you want to choose the one that has the fewest number of sig figs to get your number of sig figs for your answer. This number right here has 3 sig figs, right? The 1.4 that you're going to get when you do the subtraction only has 2. So therefore, you would only want to keep 2 sig figs in your final answer. Okay, so let's go ahead and do this. I've actually set it up for you. Let's go to the next slide and look at the answer. So here's what you get when you subtract 836.6 minus 836.2, 1.4, and that's to one decimal, and that's correct. You don't have to do anything. And then that's also 2 sig figs when you do your division. That's 2, and then this other thing here is 3, and that's 1 is 1, 0 is 1, and 5 is 1. So 1, 2, 3 sig figs here. So you've got one that has 3. This one on the bottom, and the one on the top has 2 sig figs. You have to choose the one that has the less, so 2. So your answer should only have 2 sig figs. All right, so when you divide 1.4 by 1.05 times 10 to the third, you get 1.3 times 10 to the minus third. And that is your answer here. Now, actually, to tell you the truth, I didn't do this on a calculator. So I don't know if that 1.3 is actually what they got in the calculator. And I can't stop right now, right in the middle of this. Well, actually, I could, but I don't want to. So if you want, you could just check and see. So it's possible that they actually got that 1.3, or it's also possible that they've rounded this. And maybe it was something like 1.03, sorry, 1.321 or something like that, and they rounded it. And I'm guessing that's probably what happened. But either way, it doesn't matter. You're still going to round it. If it is like 1.322 or whatever, you would still round it to 1.3 because you can only keep 2 sig figs. So the answer is actually 1.3 times 10 to the minus third. All right, so if you have any questions about sig figs or about this problem, just email me. Next slide. Which of the following are exact numbers? There are 100 centimeters in 1 meter. A is an exact number. Okay, so we're assuming that that's exact. And what that means is that we consider it to have an infinite number of sig figs. So you won't use this in limiting your number of sig figs in any of your answers. Come down to C next. Remember, we talked about this before. We said that 9 over 5 and that 32 we're going to consider to be infinite numbers of sig figs, or in other words, exact numbers. So don't use those either to limit your number of sig figs for your answer. You see what I'm saying? And if you don't understand what I'm saying here, just email me, okay, or call. But this one here is not an exact number, because if you do this on your calculator, and I have done this, you find that it's actually 1.09387, something like that. And it goes on, I think it goes on like 5 or 6 decimal places. So when they write it as 1.094, they're just rounding it off. But that's not an exact number. So B is not. Same thing here for D. Pi, if you figure it out, it can go on for page after page after page. It never repeats. People have actually done that. They've actually printed like little books with page after page after page of pi just going on and on and on and on. So anyway, it's definitely not an exact number. It's what's called an irrational number. And you won't have this on your test or anything, but just if you're interested, pi is an irrational number, which means it's a number that can't be written as a fraction. So like the real numbers are divided into rational numbers, like 1 or 2/3 or 3/4 or 5, and those can all be written as fractions. Most numbers can be written as fractions, but pi cannot. It's one of the irrational numbers. Anyway, you didn't need to know that. Next slide. So here are your answers. If you want to, you can pause. I'm going to go on to the next slide. All right, we talked about this also. Now, this is a graduated cylinder. And even if you don't take the lab, I recommend that you start trying to remember this stuff, because you're going to need it probably at some point in your life. So remember, the thing we talked about in the lecture notes was a burette. So the burettes are turned upside down. And there's a reason for that, which I'm not going to get into right now. But the graduated cylinder here is going from bottom to top. And that's the way we're most used to. So that means when we get here to 40, if we go up, we're going to be getting up to higher numbers. Okay, so look over here on the right-hand side here. Here is where our meniscus is, right here. Remember, whenever you're reading this, you want to read the bottom of the meniscus. So in other words, you want to try to find some way to bring this, and it's hard for me to draw here, but try to bring this straight across over there to your scale. And then, so, okay, what do we know for sure here? Well, we can see for sure it's more than 42 here. It's more than that. And also, I mean, I think we can also say for certain that it's less than this one, which is 43. So how many are we allowed to guess? Well, remember, we're allowed to guess one value. I guessed it's about 42.9. You might look at it and think something different, but Whatever you think it is, just write that down as your third digit. So I put down 42.9. The ones that we know for sure, the 42, we know for sure that it's 42 something, and then we're just guessing. The 9, so the 9 is an uncertain number. All right, next slide. How many sig figs are there in all these things? So here, 1, 2, 3. Here, 4. This one only has 4. Those ones right there. The 3, the 8, the 4, and the 0 are significant. These zeros are not significant. They're just placeholders. And if you wanted to, let's just take a second and do this. You could write this as 3.840. When I say take a second, it's more like 30 seconds trying to use this thing. This is what you could rewrite this as. And then you'd have to write it times 10 to the minus, third, right? Is that right? Yeah. Times 10 to the minus third. Remember, we use this e instead of having to write out times 10 to the minus. So 3.840. So if you look at this number right here, how many sig figs does this have? That's really your answer. Also, notice here, this 0 actually is significant, even though it's a 0, because somebody stuck it on here. Somebody said, okay, I've measured this all the way over to 3 decimal places here, so I want to make sure this 0 stays in the answer. So that 0 right there on the end of this number is significant, but the ones over here are not. They're just placeholders. They're called leading zeros, and they don't count. So that B would have 4 sig figs. C would have 4 because those two zeros were stuck on there by somebody intentionally. Otherwise, they would have just written 17 or 17 point. But they didn't. They wrote the zeros in there to show you that they're significant. So just remember, whenever you see zeros on the right side of the number, if it's on the right-hand side of the decimal place, then that means somebody put it in there intentionally. D is going to have how many? 1. So what they're trying to get you to do is look at that times 10 to the 8th and say, okay, 1 for the 8 here and 1 for the, 3 for that. No, it doesn't work that way. It's just 1. It's just the number in front, not the exponent. This one, E has 1, 2, 3, 4, 5, 6, 7. F will come back to. G has 1, 2, 3. H has 1, 2, 3. Because they're showing you by putting that dot there that it is significant all the way through the end of the number. This one right here, you don't know. It could be 1, it could be 2, it could be 3. If they wanted to show you that it was 3, they could have put the dot right there. But they didn't, but that doesn't necessarily mean that it isn't 3 sig figs. It just means you don't know. So on a test, you're going to have to just take your chances. I would just say it's 1. Okay. Let's go on now to number 33. You have 2 graduated cylinders. This one has 2.85 milliliters and one has 0.280 milliliters. So this one right here has 3 decimals. This one only has 2, so you can only keep the lower number, which is 2. So we can only have 2 decimal places in our answer. So add them together. Actually, this one, it won't matter anyway. It kind of would, but I mean, it wouldn't change the value. Let's go to the next slide. So when you add these together, it's down here at the bottom. You get 3.130, which is, if you write it that way, and if you write it 3.13, it doesn't change the value, right? Because the 0 doesn't change the value, but you could write it that way to show that it's significant all the way through that last 0, but you can't because you've only got the possibility to retain 2 of your decimal places. So you cannot write it this way. You have to write it the way it is on the right. Next slide. So here for 35 here at the top, we're supposed to add these together. We'll go to the next slide and look at the answer. This one here, A, that first number has 1 decimal, that one has 1 decimal, that one has 2. How many can we keep in our answer? Think about it. And then here's another, actually 2 more that are like the ones that I was talking about. So this one right here is actually a percent error. So our told you that I would remind you when we got to one. So this is a percent error. So one of these here, you've got something where you have the answer that you got theoretically, and then the other one is the answer that you got when you did the experiment. And also this problem here isn't really a percent error problem, but it's like the one that we did before, where we've got to either add or subtract a number like these two or like these two. So I recommend for all of these kinds of problems that you go ahead and do it by just going ahead and subtracting. So here you're going to get 1.6, and then I would leave it that way instead of saying, oh, there's 3 sig figs here. Well, that's actually the way that we can do it, but let's not for this one. Here also, this one is going to come out to be 0. Let's see, 0.20. So, and that last O is something that has to be left in because you want to keep 3 decimals in your answer. So when you subtract 8.925 minus 8.905, you get 0.020, and you have to keep the O. So this number right here has 2, this one has 2 sig figs. These 2 O's over here on the left are not significant because they're placeholders. But the 2 here and the O here also are significant. So here we're going to want to keep 2 sig figs in our answer because we're going to wind up with 2 sig figs on the top in the numerator here, and then we're going to wind up with 4 on the bottom. So the less of those would be 2, so we want to keep 2 in our answer. And here, what we're going to wind up with is when we do our multiplication here, you have 4 here and you have 3 here, so you would keep 3. And then you're going to be dividing by 2, so you want to keep 2 in that answer also. Now, usually though, let me just say this, we usually wouldn't go through all this because it's a lot of work. So, I mean, and it's okay for this kind of a problem, but if you just have a problem where you're doing a lot of like just chain multiplying and dividing, then the easiest way to do it is just to say, okay, let's go through all the numbers we're going to be multiplying and dividing, like here it would be these two, and figure out which one has the fewest number of sig figs, and then use that as our basis for our final answer. And that's the way you're taught to do it at A&M and UH. And also most other textbooks will tell you, don't round your calculator, just leave all the values in your calculator until you get your final answer. So if you do it that way, then at the very end, you take all the digits you have in your calculator and round back to the number of sig figs that's the lowest number in all of the numbers that you started with, which in this case right here, if you're just multiplying the 6.404 times 2.91, it would be 3 because 2.91 has 3. And if all this is confusing you, just email me but really remember that the only time it's really going to matter is going to be on the problem or two they give you on the final, where they say, do this problem to the correct number of significant figures. And then for the rest of them, you know, I mean, the ones that I grade, I'm not going to count off. Okay. So I mainly want you to get the right answer, but I'm not saying it isn't important. Okay. Let's go on to the next slide. So when we add these things up in number 35 up here at the top, this is what we get when we first do the addition. But notice here, we only have 1 decimal place in these top 2 numbers, so we can only keep 1 in our answer here. So we're going to have to round this back. So since this number right here is more than 5, we're going to raise the next one up to the next number, which is 10. So that means that we actually then have to add 1 more over here. So this is going to become 641.0. Down here on the bottom, when we do this here, we get 1.6, which has 2 sig figs. So we want 2 sig figs in our answer. So what we're going to wind up doing is we're going to multiply this times this. And it doesn't really make any difference. But The way they want you to do it, and the way that I did it here, was I multiplied these, and then let's see, where is this one? F. Oh no, B. Okay, so I took and I left the number 18.63564. That's what I got. Yeah, that's what I got when I multiplied 6.404 times 2.91. I got 18.63564, and I just left it. Now, the way Brown and LeMay would do it is they would, at that point, then, and see, this is why people don't usually do it this way. So, because it just takes too much time. So then they would say, no, we can't leave 18.63564. We got to round that back to 3 sig figs. So they would round that all the way back to 18.6. But you're losing a lot of data there by doing that. I mean, you're rounding, you see what I'm saying? So that's why most people don't do that. In fact, Brown and LeMay is the only book that I know of that does it. I'm not saying it's the only one that does it. I'm saying it's the only one that I know of. So, but the way that they would do it is they would round it all the way back to 18.6 and then divide that by 1.6. And the answers will be similar, but there's going to be a difference there. So I recommend that unless it's one of these problems like this one right here, one of these percent error problems, or as I said before, if they specifically want the right sig figs. Otherwise, I would just leave all these values in your calculator. Just leave them in there and divide by 1.6. And then when you get your final answer, which is this one, then round it back to 2 sig figs. So to do that, I mean, and you have to round. This makes the 7 go to 8. This makes the 2 go to 3. But this one doesn't change 7, so 7 stays. 7 makes the 4 go to 5. 5 makes the 2 go to 3, but 3 doesn't change the 6. 6 makes the 11 here go to 12, and then you're done. So you only have to really round at the end of the problem. Let's go on to the next slide. To convert from centimeters to millimeters, you would just multiply 8.43 centimeters times your conversion factor. So your 8. I get so frustrated when I try to write this stuff out because it just seems like I'm wasting everybody's time. So I'm only writing when I think it's really necessary. And then times your conversion factor. So it's 8.43 centimeters. I didn't write centimeters. So let's just try to put that in real quick. Centimeters. It's just so awkward. I don't know why they... Okay, and then you want to put in your conversion factor, and you want on the bottom what you have over here. This, you want to be on the bottom over here. So write centimeters, and then what's the other thing that you're trying to convert? Millimeters. So write that on the top. So your answer is going to be in that. And the centimeters, and I didn't get that very good, but centimeters here and here are going to cancel. And then what's your conversion factor? How many millimeters are in 1 centimeter? 10. So, I mean, you don't have to look this up. You just remember. So what you're going to wind up with is 8.43 here times 10, which is 84.3. And that's going to be in millimeters, right? I'm just going to write it 1m here. So that's your answer there. And then you do this one the same way, E, 235.3 meters. But your conversion factor for E is going to be 1,000 millimeters over 1 meter, right? And the reason is because 1 meter is the same thing as 1,000 millimeters. So the answer is going to be 235,000 over here, 300 millimeters. Or if you want, if you're understanding this well enough to do it, you can just move the decimal place over 3 places to the right, which means you add a 0 here and a 0 here. Right, so you've got 235,000 either way, or if you 235,300, or you can write it as 2.353 times 10 to the 1, 2, 3, 4, 5. So either way, I mean, I'd like to write all this out, but it'll just drive us all up the walls. So let's go to the answer. Next slide. So this is what I would have written out if I'd written it out. So 235,300 which is fine. I mean, if you want, you can leave it like that, uh, at least for my tests. Uh, and the only thing is, if it's a multiple choice question, they may change it and make the answer so that it looks like that. So you can just say, okay, well, that's the same thing. So 2353E5 are times 10 to the fifth. These are both the same number, it's just written in a different format. If it's a short answer question, if you want, you can just leave it like that. Next slide. The circumference of the Earth is 25,000 miles at the equator. What is the circumference of the Earth in kilometers? So here's your conversion factor. So, I mean, I will just take a second for you and do this. So 25,000 miles is what you're given to start with. I mean, if you can read this. And I'm also making this too big, so I'm going to run out of room. So let's just set up the first conversion. So we want to multiply this times some fraction that's going to convert this from miles to kilometers. And we are given that. Now, I didn't write this, but this is miles. M-I, miles. So we want miles down here in the bottom. So they'll what? Cancel. So we want our conversion factor, which is like multiplying by 1, and we want to know how many kilometers correspond to 1 mile. So our conversion factor here says that for 1 mile, so right, 1 mile, we have 1.6, let's just call it 1.6 kilometers, just to save all of us some agony here. 1.6 kilometers. The miles cancel. I'm already doing the rest of the problem. I'm trying to write this. The miles cancel, and we're left with our answer in kilometers, which is the answer to the first part here. That's what they want. And even if they didn't, we'd have to do it this way. So you just take your calculator, multiply 25,000 times 1.6. Then whatever you get for that part, it's going to be in kilometers. To do the second part, you just multiply by 1,000, or you can do the thing again where you take a parentheses and make a fraction, and in that case you'd be writing 1,000 meters on top, and I think it's on the answer on the next slide, and 1 kilometer on the bottom, and then the kilometers at that point would cancel. Okay, so, or you can just, whatever the answer was that you got over here, you can just multiply that by 1,000 if you understand it well enough to do that, or you can also just move the decimal place over 3 places to the right. We'll look at the answer to that in just a second. Let's come down here and do this one. A single capsule weighs 0.65 grams, and he weighs out 15.6 grams. So just divide how much he weighed out, your total mass here. So divide 15.6 by 0.65. And then we'll take a look at the sig figs here in just a minute. Divided by 0.65. So take your calculator and divide that. And I forget what it is, but I think it's 40, but I'm just going from memory. Or maybe it's 24. Anyway, I'll get to the answer in just a second. Whatever it is, how many sig figs can we keep here? Well, we're dividing. We've got 3 sig figs on top and 2 on the bottom. So how many can we keep? Think about it for a second. We can keep 2, right? Because this one on the bottom only has 2 sig figs. So that means, and actually, let's go on to the, do I want to say anything else here? All right, let's go on to the answer. Down at the bottom here, I think we can dispense with this one. I think the one on the top's okay. Oh, okay, it is 24. So, but it came out exactly 24. So, and we said we can keep 2 sigs because this thing right here has 2 sig figs. So we can actually keep that. But let me ask you this, and this is one of the reasons why sig figs can be a real pain in the butt. What if we only had 0.6 here and we got 24 for the answer? I mean, we wouldn't, but just say we did. Then we'd have to round it back to 20. because we've got only one sig fig at that point here. Now they made it so it didn't happen that way, and they intentionally did that because they didn't want to make you start thinking, wow, you know, these sig figs can be a real drag, uh, because they can, and we'll see that in the next problem too. If you had zero point 0.6 here instead of 0.65, and you came out with 24, you'd have to round that 24 back to 20 because you could only keep one sig fig. But it isn't 20. It isn't. It's 24. You see what I'm saying? So you're getting the wrong answer, basically. Let's go to the next one. I'll show you something else. So look up here at the top. 65 kilometers per hour. So to do this one at the top here, what you have to do is you have to convert, you've got kilometers per hour. So what you want to do is get it in miles per hour. So the hour is okay. You don't have to do anything with the hour. It's fine. You just have to change 65 kilometers to miles. We already did a problem where we did that. And here is our conversion factor right here. So this is the same thing we've already done. So I'm not going to spend any time on that. When you multiply these two numbers here together, this kilometer is going to cancel with this one. You're going to get your answer in miles. And it's going to be 40.391 here. And so the question is saying, would you violate a speed limit of 40 miles an hour? Well, okay, so over here we've only got two sig figs, right, on the 65, so we can only keep two here. So we round this, that becomes 9, that becomes 4, and then that stays as 0. So you get 40 here when you round it to the correct number of sig figs. So your answer is no. But look at the real answer. The real answer is 40.391, and the answer would be yes. So that's why I think a lot of textbooks tell you this is how you do sig figs. And then by the time you get halfway through, or maybe not even that far through the rest of the book, I mean, I've noticed this in my physics books. They just kind of like, I mean, let me just take a second and talk about this because I know it's probably discouraging you. And you shouldn't let it discourage you because it really doesn't matter because I'm not going to count off for it. Oh, either on your exams that you have during the semester or on the final. So you just don't have to worry about it other than there's going to be one problem on the final where they're going to say do this problem and do it to the correct number of sig figs. I guarantee you there'll be one. That's 2 points. So just remember it then. Let me just say this. I've noticed that the physics textbooks do that they tell you this is how you do it, but then they don't do it. Like they quit. And I've also read people like who have written things on the internet, and they'll say, you know what I'm going to do? I'm going to just round everything off to 2 decimal places. And the hell with I mean, pardon my language, but I mean I usually don't curse, but that's kind of the way some people feel about this stuff. Is just the heck with it. I'm just going to round everything to 2 decimal places. Okay? I mean, forget all of this crap. Okay, so anyway, I hope I haven't like upset anybody. I know if I did, I didn't mean to. So we're going to do everything just as I said. For those problems like the one on the final that you'll inevitably get, and also the ones where you do the percent error, those really lend themselves to doing them in 2 steps. So do the adding or the subtracting first, find your number of sig figs, and then use that in your answer. For all the other problems, if I were you, knowing that this is the way it's going to be at your undergrad or your grad institution, just do everything, leave all the digits in your calculator until the very end when you have your final answer, and then round that, okay? All right, so I think that's the last time I'm going to talk about sig figs this semester if I can help it. Okay, let's go on here to B, and I didn't talk about this before, but we've already done these. Convert the following Fahrenheit temperature to centigrade. So let's see if you remember the answer to that. Remember I told you you might want to memorize there's one temperature where these are the same and it was minus 40, right? So you wouldn't even have to do this problem. You could just write down the answer. So it's minus 40, and then we also want to convert that to Kelvin. So to convert it to Kelvin, you just add 273 to minus 40, and you get 233 Kelvin. And the way that you write your answer in Kelvin is not degrees Kelvin. And I've had People explain that to me like 10 times and I still don't understand it. But evidently Kelvin is not really like a temperature scale in the sense that centigrade and Fahrenheit are. It's some different kind of an entity, so you aren't supposed to put degrees Kelvin. You're supposed to just write Kelvin, so that's what they did here. So the answer is 233 Kelvin. Let's go on. Um, let's see, convert the following Celsius temperatures to Kelvin and to Fahrenheit. All right, so I'm not going to actually go through this because we've done it already. You just want to, first of all, multiply that by 9 over 5 and then add 32. And that's going to give you your Fahrenheit degrees, your degrees Fahrenheit, which I write this way. Okay, so again, you would multiply minus 25. You leave the minus sign in there. Multiply it by 9 over 5, which that's going to be minus 45. And then add 32. So minus 45 plus 32 is going to be 13, I think. Let's go to the next slide and see if I get it right. Yeah, it's going to be minus 13 degrees Fahrenheit. So again, you just multiply by 9/5 and then add 32 and you get minus 13 degrees Fahrenheit. And then again here, you can read this at the bottom. Go ahead to the next slide. All right, now we're getting into the ones that are a little bit more interesting, and these are the ones, I think this one and maybe two more after this are the ones I like to ask on tests from chapter 1 for your short answer part of your test. So your tests have multiple choice questions, and then they have short answer questions. A material will float on the surface of a liquid if the material has a density less than that of the liquid. Given that the density of water is 1 gram per milliliter, we want to remember that. Will a block of material having a volume of this many cubic inches and weighing 350 pounds float or sink? Now, if they gave these to you in the units that you want them to be in, like if they gave this to you in cc and they gave this to you in grams, all you have to do is just divide it and compare it to 1. If it's more than 1, it'll sink. So this is what I was telling you earlier. A lot of the problems here, like almost sometimes like more of the problem is converting all of these things to the units that you want them to be in. So here, what we need to convert 350 pounds to grams because we want to get this in grams per milliliter. We want to get the density of this block in grams per milliliter. So remember, we have to do this thing here in 2 steps. Or, I mean, you could do it in 1, but either way, it's going to wind up somehow being 2 steps. You first of all want to convert the pounds to kilograms. And then you want to convert the kilograms to grams by multiplying by 1,000. So that second step's an easy one. So what you want to do is multiply 350 pounds times however many kilograms are in a pound. So that's going to go in parentheses with a line across the middle, make a fraction or something in the top, something in the bottom, and that's your conversion factor. Get it to kilograms and then multiply that by 1,000 to get it to grams, and you're done with that part. And then the bottom part for the volume, you want to convert from cubic inches to cubic centimeters. And the way you do that is you have another conversion factor. We haven't used this one yet, but the way that you do this one is you say, okay, 1 inch by definition is 2.54 centimeters. So if you have a cubic inch, you have an inch this way, an inch that way, and an inch up and down. You've got 2.54 centimeters in each of those 3 directions. So the volume there is going to be 2.54 times 2.54 times 2.54, which, if I'm remembering correctly, is about 16 centimeters to the 3rd power in 1 inch to the 3rd power. Or in other words, every one of these things right here is going to be about 16 cc's. So to convert this one, we just multiplied this number right here by this. It's actually not exactly 16, and you would want to use the exact number, which I'll see on the next slide, show it to you on the next slide. So whatever the exact number is, you just multiply it times 1.2 times 10 to the 4th, okay? And then that's going to give you your answer in cc's. Then whatever you have there will go, like you'll divide that into however many grams you got over here when you converted 350 pounds into kilograms and then into grams. So let's go ahead and go to the next slide. So, I mean, don't panic when you see this because it's not really a big deal. Just kind of like have everything crammed in here. So let's start off with the pounds thing. So first of all, before we do anything else, that little thing right there that looks like a number sign is a abbreviation used in the United States for pound. And the reason that I use it sometimes is to save space, so that I could get all of this stuff on one line. So if you can't remember that, I've got it written over here. So that hashtag thing is pounds, and then you multiply it times your conversion factor. So here's your conversion factor right here, right? And you want your pounds here in your conversion factor to be on the bottom so that they'll cancel the ones here on the top, and you're left with an answer in kilograms. Now, we don't want kilograms, we want grams, but that's not going to be too hard to do once we get it to kilograms. So what you're in essence doing is you're dividing 350 here by about 2.2 here. It's 2.20462, but so do it, you put in all the digits. So in your calculator, just divide 350 by 2.20462, and that's going to give you your answer in kilograms. Okay. And then, so when you do that, I didn't actually, oh yeah, I did. Okay. So it's about 159 kilograms. And then I multiplied that by this second conversion factor here, which is just to convert it to grams. Or you could have just moved this decimal place right here over 1, 2, 3 places, and it's going to give you the same answer. 158,757.5183 grams, which I wrote it in scientific notation here. So I wrote it as 1.587 blah, blah, blah times 10 to the 5th grams. Okay, so that takes care of our mass. And then for our volume, we start off with the number of cubic inches they gave us in the problem statement here. And here's the conversion factor. Okay, so I told you how to do this. So if you have a problem on a test and they didn't give you this conversion factor, which they should have, but if they didn't, you could figure out the 16 right here, right? The way I said before, which if you remember was you multiply 2.54 times 2.54 times 2.54, and that gives you, and you can try it in your calculator if you have a second, you should get about 16.39, and that's where this thing right here came from. But they'll probably just give it to you. Okay, so anyway, and again, you want to put these in so that the inches here, over here on the right-hand side, these inches, they have to go on the bottom. So you want it to be how many cc's are in 1 cubic inch, or however you do it, but you want the inches to the third to be on the bottom so they'll cancel, just as always. So your answer here is going to be in cc's. So you multiply 1.2 times 10 to the 4th, and don't forget the 10 to the 4th here. It's easy to just multiply 1.2, but you'll get the wrong answer, times 16.387 and so forth, and you get 19.66. And notice this is times 10 to the 4th there. Don't forget that E4. And this is your volume. So here's your volume, here's your mass. So all you have left to do now is just divide the mass here in grams by the volume in cubic centimeters, and you're finished. So when you do that, that's done down here at the bottom, actually right here. And when you do that, you get 0.8 approximately grams per cc. And you can go ahead and you can round it off if you want to, but they're asking us, will it float? So let's go back up here. Will a block of material float or sink? And so here's our answer. It's 0.81 grams per cc. How much is water? 1 gram per cc. So which is lighter? This is lighter right here. So it will float. Okay, let's go to the next one. Another one of my favorite problems. A star is estimated to have a mass of 2. There's actually one that's even better than this one. I like problems that deal with stuff out in the universe. A star is estimated to have a mass of 2 times 10 to the 36 kilograms. How many sig figs do we have here? 1. So what does that mean? Well, it means we're going to have to round our answer to 1 sig fig, right? So let me just say this. This is probably the only time this is going to happen in all of general chemistry. But anyway, just let's go ahead and go on. So assuming it to be a sphere with a radius of 7 times 10 to the 5th kilometers. So you remember the problem just a second ago we did where I told you that sometimes it's harder to get it in the right units than it is just to do the problem. And remember the one we did where we had to convert pounds to grams and all that? It was more work by far just to do those conversions than it was to do the problem. And that's the way it is here, kind of. So maybe not quite as bad here. So what we need to do, actually it is, because we have to get okay, let me just stop here. What do we need? So let me just let you look at this for a second. What do we need to do? We need to get the density. So what they're asking for is the density here. So can you remember what is the formula for density? Just think about it for a second before I tell you. What's the formula for density? Mass per volume. What are they giving us here? Are they giving us the volume? Right there, is that the volume? No. So what do we have to do? We have to figure out the volume. So if you figure out how many meters, this number right here, this 7 times 10 to the 5th, see that number right there? If you convert that to meters, well, that's good. That's part of what you need to do. And then you'd have to then go ahead and do it to centimeters because they actually want this in centimeters. But you haven't got the volume. So I'm just saying this because I see this happen on exams. We do want the radius in centimeters, but that's not what we want at the end of the day. What we want is the volume. So what is the volume in terms of the radius? So think about that for a second. So what do we have here? What kind of a shape do we have? We have a sphere. So the volume of a sphere is 4/3 times pi. Wait for 15 minutes now while I write this. Times pi r what? Is it r squared? No, that's the area of a circle. The area of a circle is pi r squared. The volume of a sphere, like this, is 4/3 pi r cubed. So first of all, we do have to convert this number to centimeters because we have to get our answer in centimeters. So, I mean, then that's not trivial because that's 2 steps. But then once we get the radius, then we have to substitute it in right here and then figure out what the volume is. And the volume is going to be in cubic centimeters. And then we also have to convert this number right here to grams. But that's easy. We just multiply that by 1,000. Now that actually is hard to read because it looks like I cut it off. But this is actually supposed to say 2 times 10 to the 36 kilograms. So it would be 2 times 10 to the 39th grams. Excuse me. So this one is pretty easy. So first of all, before we can do this formula for the volume, we have to convert 7 times 10 to the 5th kilometers to centimeters. We want this to be in centimeters here before we plug it in here. So to do that, you can do it in 2 steps if you want. And maybe you should do that at least at the beginning of the class until you get used to it. So I would do it like convert it from kilometers to meters. And that means you multiply by 1,000, as you already know. And then after you do that, you'll have your answer in meters, right? And then convert meters to centimeters by multiplying again by 100 because there's 100 centimeters in every meter. In every meter. And then you're going to get your answer in centimeters, which is what you want. It's going to be, I mean, I'll just tell you, it's going to be 7 times 10 to the 10th centimeters. This is going to convert to 7 times 10 to the 10th centimeters. Or if you want to do it in steps, it's 7 times 10 to the 8th meters, which in turn is 7 times 10 to the 10th centimeters. So we're going to put 7 times 10 to the 10th centimeters here. And I'm not going to write out the centimeters because for some reason it takes even longer to do the letters than the numbers. So it's centimeters. So put that in where R is. So what that means is that this number right here has to be raised, this whole number has to be raised to the 3rd power. to get our volume. And even when we get the volume, we're still not done, but we're almost done. So that means you have to raise 7 here. This 7 has to be raised to the third power. So that's 7 times 7 times 7, which is 49 times 7, which is 343. And then you have to raise this number here. The exponent part also has to be raised to the third power. So the way you do that is you add exponents. So it's e to the 30th. It's 10 plus 10 plus 10. So 10 to the, 10 to the 10th raised to the third power is 10 to the 30th power. So you're going to get 343 raised to the 30th power. Okay. That's what you're going to get for this part right here. Then so you have to keep track of this stuff. And if you're trying to do it all in a calculator, if you screw one little tiny thing up, it all goes down the drain and you have to start over again. So when you get these really crazily complicated problems, I recommend every time you do this stuff, you just write down what you got, so that you don't have to keep starting over. And it happens to me too, and I've been doing this for a heck of a long time. It's partly because my calculator is crap, but it's not just that. It's sometimes I just do stuff that causes me to accidentally erase the answer that was in there. Anyway, so you can do it however you want. I recommend when you're typing this stuff in your calculator, you do it really carefully and slowly. And I would also on an easy problem, it's not a big deal, but on a hard problem like this one where you've got all this stuff you have to do, like when I got right here to this step right here, I'd write that down. I'd write down 343 times 10 to the 30th. I'd write it down. So I know this is what I got when I got r to the third power is 343 times 10 to the 30th, or you could write it as 3.43 times 10 to the 32. And write that down before, and then in your calculator, you can leave the number in your calculator and then multiply it by 3.14, which is pi. Or if your calculator has pi on it, you can just multiply it by pi. And then you still have to multiply it by 4/3, which if you want to make it easier, you could either multiply by 4 and divide by 3, or you could just multiply by 1.333, which is the same thing as 4/3. And then you're done. Okay, so whatever you get after all of that is going to be your volume in centimeters to the third. So I'll just write that out here. But that's not your answer. So what they'll do on the test is, what they may do is they may write down this number that you just got here for your volume as one of the answer choices. And if you forget, oh, but that's not the answer, that's just the volume, right? Then you'll miss all that work, will go down the drain, and you'll miss the question. So we don't want the volume, we want what? The density over here. So the final answer, we're almost there, would be 2 times 10 to the 39th grams divided by whatever we finally got over here for the volume. Okay, and then that would be the answer. Again, this problem right here, about maybe 90% of the problem is just trying to get it in the right units. Okay, so we're right at an hour here, and I don't really like going much over an hour if I can help it. So this, and even if we weren't right in an hour, I was going to let you guys just look at number 75 on your own. And also, I'm going to go to the next slide for just a second. Again, don't panic when you see this. Just read it one line at a time. This is figuring out what the mass was. And then this part right here is figuring out what the radius was. This line here is figuring out what the radius is in centimeters. And then these two lines here are figuring out what the volume is in cubic centimeters, and then this line down here too. And after we did all that, holy mackerel, this is what we got for our volume. And then all we have to do is take this number in bold here, which is the mass, and divide it by the volume here in bold, which is 1.44 E33. And we get, after all of that, 1.392 times 10 to the 6th grams per cc. Whoa! Which, if you round it to 1, remember we said we're going to have to round this to 1 sig fig, right? So this will actually round to 1. So 1 million, holy mackerel. So think about that for a minute. Water weighs 1 gram per cc, and this star has a density of 1 million grams per cc. So anyway, then at the bottom down here, I'll let you guys look at this on your own. Let's go to the next slide. And this one also, and it's not just because we're over an hour, but this one also I'd like for you just to do on your own, because it's kind of a fun thing. And and then also these here, these are the kind of things that you can just look at. All right, now here's another problem that I like to ask for short answer questions. A column of liquid is found to expand linearly on heating 5.25 centimeters for a 10-degree Fahrenheit rise in temperature. If an initial temperature is 98.6, what will the final temperature be if it's expanded by 18.5 centimeters? So every time this thing heats up 10 degrees, this substance, this liquid, goes up by about 5 centimeters. So in other words, if you look at it, if you look at how high did it go up, and if you basically divide it by 5, then that's going to tell you how many times it went up 10 degrees. So what I'm saying is if you divide the 18.5 by the 5.25, that's going to tell you how many times it went up by 10 degrees. Well, 18 divided by 5, it's a little over 3. It's about 3.5. So that means 3.5 times 10, it's gone up by about 35 degrees. But that's not the answer to the question, because that's not what they were asking. They're asking, what's the final temperature going to be if it went up? If it went up by 35 degrees, but it started at about 99 degrees, at about 99, then you have to add that. So that's about 134 degrees for your answer. Okay, so the good news is that I don't think we have any more problems that are as horrible as the ones that we just did a minute ago. So again, to do this problem, all you have to do is divide 18.5 by 5.25, and that's going to tell you how many times it went up by 10 degrees. So then it's about 3.5. So take the 3.5 and multiply it by 10, and that tells you how many degrees it went up in temperature. So that's your change in temperature. But they don't want that. They want the final temperature. So you add your change in temperature to what it was when you started, which was about 99. Next slide. All right, so when you divide the 18.5 by the 5.25, you get about 3.5, which is what I said. Multiply the 3.5 by 10, and you get about 35, which again is what I said. And then add that to the initial temperature, which was 98. Now, for the sake of time, and when you do that, you get about 134, which is again what I said. So this is not difficult at all. You just remember, divide this number by this number, and then multiply it by that number, and then add it to that number. And then the second part is they also want you to convert it to degrees centigrade, but you know how to do that, right? You're supposed to, so just let's see, first of all, you would have to subtract from this. You subtract 32 and then multiply by 5 over 9. And when you do that, you get 56.6 degrees centigrade. Next slide. All right, this is one of these error problems, which you're going to start off with, and it doesn't really make any difference here, but the true value is 2.7. The reason I say it doesn't matter is because you're doing the absolute value here. So if you get it, if you subtract this one from this one, or if you subtract this one from this one, one of them is going to be, the number's going to be the same. One's going to be plus, one's going to be negative, but when you take the absolute value, they're both going to be exactly the same. So, but you're supposed to do it by doing this number right here. Notice it says here the true minus the experimental. So take this one right here minus that. So that's going to be 0.06. And that has how many sig figs? So think about that for a minute. Let me go ahead and keep going. We're going to divide that by the true value here, which is this number right here. Right then, so when we subtract 2.70 minus 2.64, we get 0.06. That has only one sig fig. So you're going to wind up with 0.06, and then you're going to divide that by 2.70, which has 3 sig figs. So let's go to the answer. So 2.7 minus 2.64 is 0.06 divided by 2.70, which is your true value, and that gives you 0.0222. But because we've only got one sig fig right there, we have to round this one back to here and this one back to here, and we end up with our final answer 0.02. And then we multiply, to convert to percentage, you multiply at the end by 100% and you get 2%. Okay, so the answer done the way that I really want you to do these is 2%. Next slide. This is my favorite problem out of this whole chapter. So unfortunately, we're kind of short on time. So let me just set this up for you real quickly. Then I'll show you the answer. Let me read it first. Sterling silver is a solid solution of silver and copper. If a piece of sterling silver necklace has a mass of 105 grams and a volume of 10.12 milliliters, calculate the mass percent of copper in the piece of necklace. Assume that the volume of silver present plus the volume of copper equals the total volume. And then it says refer to table 1.5. That's to get these two values for these two things right here. So I just wrote those in for you. So, I mean, really the key here, there's a couple of things. First of all, there's only two things in this necklace, silver and copper. So we need to remember that. So that means if we add their masses together, the mass of the silver and the mass of the copper, if we add them together, we're going to get that. And if we take the volumes and add them together, we're going to get this. So there's really an easy way to do this, but there's only one way to do it. And if you try to do it any other way than the way I'm getting ready to tell you, you're not going to be able to do it. And you're just going to get frustrated and waste time. So please, either go by what I'm getting ready to say now or look at the answer to get ready, because this will almost certainly be on your test. So what we're going to do is we're going to start off by saying that the mass of the silver plus the mass of the, instead of writing this as AG, I'm just going to put S to make this less tedious. And that's supposed to be an M sub S. So the mass of the silver plus the mass of the copper equals what? So look at the problem statement while I'm trying to write this equal sign. What's the total mass? That's right here. It's 105.0. I'm just going to write 105. Just because this is just, it's almost like torture. 105 grams. Okay. And then what's the other thing that we know? Let me just, since we've got lots of room, because believe me, I need it. The volume of the silver, and you really wouldn't write this way. Instead of silver, like S, you were supposed to write AG. But I mean, we might be here all day waiting for me to write AG. So the volume of the silver, that's wrong. The volume of the silver plus the volume of the copper equals what? 10.12. Now, it turns out that that top equation, well, I'm going to talk while I write here. Maybe someday somebody will explain to me how to do this a better way. This equation here on the top is actually the one that we're going to use here to solve the problem. So that's supposed to be 105 grams. The mass of the silver plus the mass of the copper is 105 grams. We could actually do it either way, but let's just do it that way. And then also we know that the volume of the silver plus the volume of the copper is 10.12 milliliters. Now it looks like we got two equations here. So if you try to do this where you say, okay, let uh, MC be X and let VC be Y, you can't do it because you really don't have two equations here. What you actually have is one equation. So we need to get this down to one unknown. And if you don't have even the slightest idea what I'm talking about, don't worry about it because we're going to figure it all out here. So what I'm saying is that we need to get it so that we can write this and this in terms of X, where we're going to use X for an unknown. So look at these two things right here. Do you remember what we said about density? First of all, what's the formula for density? Well, the formula for density is mass per volume, right? But we also said something else. If you remember, we said that we can rearrange that so that we can write it mass equals the density. Let me make sure I've got, yeah. So mass equals the density times the volume. If you don't see that, just take the original formula. Density is mass per volume and rearrange it. Multiply both sides by volume. You get mass is the volume times the density. So what we can do here is we can substitute in here for both of these by saying, for example, instead of the mass of the silver, we can say the volume of the silver times its density. And instead of the mass of the copper, we can say the volume of the copper times its density. So, well, we know the densities because we see them right here. So here's the density of copper. It's 8.96 grams per cc. And here's the density for silver. But what else do we need? We need the volume. We don't know the volume. But look, this is the key to the whole problem here. This is what we do know. We do know that the total volume is 10.12 milliliters. There's only two things that add together to get that. So here's the trick. I'm going to write that the volume of the silver is X, and I don't know if this is the way it is on the next slide or if it's the reverse, but it doesn't matter. It doesn't matter because you're going to get the same answer either way. Now let me ask you this. What's the volume of the copper? Pardon that V there. You're probably thinking to yourself, it can't be that hard, but it is. Believe me. Okay, so that V is way bigger than the other one, but anyway, so if the volume of the silver is X and the total volume is 10.12, and there's only two things in there that have to add up to 10.12, then what does the volume of the copper have to be? Okay, it has to be 10.12 minus what? It has to be. So what we can do is we can rewrite this equation, which instead of making you have to agonize over this, I'm just going to go to the next slide. But we're going to rewrite this equation right here. Instead of writing it as the mass of the silver plus the mass of the copper, we'll write it as the density of the silver times the volume of the silver, which we're just going to call X, or at least I think that's how it is. And then plus, for the copper, it would be the density of the copper, which is right here, times the volume of the copper, which we're calling 10.12 minus X. Now, on the next slide, I might have them reversed, but it doesn't make any difference, right? And what does it equal when we add these together? 105 grams. Okay, so let's, without any more ado, let's go to the next slide. All right, so here is our equation, and you can actually read it now. And it's in the right subscripts. The density of the copper times the volume of the copper. This is the mass of the copper. Remember, mass is density times volume. Plus the mass of the silver, which is the density of the silver times its volume. The key to the whole problem is we're going to substitute X here. And I think this is reverse of what we did before. It doesn't matter. And then, so this one here has to be 10.12 minus X, because when we add them together, they have to add to 10.12. This is the key to the whole problem. If you don't do it exactly this way, you can't do it. Okay, I mean, I don't mean exactly this way in terms of which one you call x. That doesn't matter. But what I mean is if you start trying to set this up as two equations and two unknowns, it won't work. Okay, so just be warned. Okay, so anyway, so all we have to do is substitute in the two values for the densities, which we saw on the previous slide. And then for this one, we put x, and for this one, we put 10.12 minus x. And then you only have one equation, but you only have one unknown, and that unknown is x. So if you didn't know this already, this is like something you learn in math, in linear algebra. If you have one equation and one unknown, you can solve it. But if you have one equation and two unknowns, you can't solve it. You have to have two equations and two unknowns, or three equations for three unknowns to solve them. In other words, for every independent equation you have, you can only have one unknown. So, but we can solve this one because we've only got one unknown, and that's the x. So when we solve for x, which is done all the way through this part right here, we get that x is 0.818 cc's. Then we look back up to see what we said x is. So right here we said let x equal the volume of the copper. So if the volume of the copper is 0.818 and the total volume was 10.12, then if we subtract 10.12 minus the 0.818, we're going to get the volume of the other thing, which is the volume of the silver. And then we can multiply those respective volumes times their densities and get their masses. So originally what they wanted to do is, they want us to get, up here at the very top, they want us to get the mass percent of copper. So we'll have to figure out the mass of the copper and then divide it by the total mass. The total mass was 105. So we really wouldn't have to do the part for the silver, although it's an interesting exercise. But anyway, so multiply, let's see, we want the copper. So copper is x here. So x here is 0.818 cc's. That's the volume. So if we multiply that by the density of copper, which is here, which is 8.96, we get, and also it's here, multiply these two together, we get 7.33 grams of copper, and then divide that by the total mass, which is 105 grams. And that's done right here. So 7.33, which that just comes down here, divided by the total mass, which was given in the problem statement, 105, and you get a fraction or decimal of 0.06980952, and then multiply it by 100, move the decimal over 2 places to the right, 6.981. Look, anyway, that's the percentage. And you can stop here. I mean, because on this kind of a problem, I'm not going to count off for sig figs. So 6.981%, and actually it looks like that's the right number of sig figs too. So look with me back up at the problem statement for a minute. We've only actually got two numbers here, that one and this one, and they both have 4 sig figs, so we can actually keep all 4 of those. So that's pretty neat. All right, so this problem you can just about, mark it down and give it a gold-plated guarantee. It's going to be on your exam. It's going to be one of your short answers, so it's going to be one of the ones that counts a lot. So please be sure you know how to do this before you come to the exam on whatever day we take the first exam. Next slide. All right, so I've already gone an hour and 18 minutes, and I didn't have the same problem this time that I did on the lecture notes, so I'm going to keep going. So let's try to go through these multiple choices really fast, because we've already done all of this stuff before. Which of the following has the same number of sig figs as this number right here, right? So count them with me. 1, 2, 3, 4, 5, 6, right? You agree with that? That last 0 there after the 1 before the question mark is significant, isn't it? Because it's stuck in there even though it didn't have to be. It's not a placeholder. Somebody intentionally put that there. It's on the right-hand side of the decimal place, so it is significant. So there's 1, 2, 3, 4, 5, 6 sig figs. So just looking through here, 4, 1, 6. So there's our answer. 3, and that one could be either 1, 2, or 3. So on a test, I recommend you choose 1. Answer C. Next slide. And there you go. Next slide. All right, round this one to 4 sig figs and then express in scientific notation. That means write it as a number between 1 and 10 and then multiply it times 10 to some power. All right, so 229.613. So to get it to 4, we have to get this one, this one, this one, and this one. That's all we want. So the 1 and the 3 have to go. We're going to have to give them the boot. So start all the way at the right-hand side. 3 is less than 5, so it doesn't change the 1. So we leave the 1 as 1. So let's just mark out the 3. And then the 1 is also less than 5, so it doesn't change the 6. So just mark it out too. Now what have we got? 229.6, but they want to write it in standard exponential notations. So you want to move the decimal place over between the 2 and the 2. You want it to be a number between 1 and 10. So move the decimal place 2 places to the left. You're making that number smaller when you do that, so you want to make your exponent larger. Every time you move the decimal place over 1 place to the left, you're multiplying it by 10 to the 1 power, or times 10. So because you did it twice, you're multiplying it by 10 to the second. You're going to have 2.296 times 10 to the 2 power. 2.296 times 10 to the 2, which is going to be this answer choice right here. Next. All right, next. All right, now this problem right here, I'm just going to tell you ahead of time, you have to actually write these out. You're going to have to convert both of these. So convert cc's to meters to the third. And then you're also going to have to do the other thing. Before we do the other thing or talk about it, let me just say this. In general, this isn't hard, but you can't do it in your head, which means you have to write it out. So you're going to have to do 2 things. You're going to have to convert 3 things. Convert the centimeters to the third to the meters to the third first or second, and then convert the grams to kilograms, and then do your division. And that's the only way you can do it. So if you try to do it in your head, you're going to get totally confused, or at least I do. So to convert from centimeters to the third to meters to the third, we have to remember our conversion factor. cc's, how many cc's in a liter? So that's why I recommend you memorize this stuff. Those two, anyway, 1,000 cc's is 1 liter. Or you can remember it 1,000 milliliters is a liter. That's easier. And then how many liters are in 1 cubic meter? Do you remember? It's the same, which is why I showed you those 2 slides in the lecture notes with the pictures. It's the same. So if there's 1,000 centimeters to the third in a liter, and if there's 1,000 liters in a meter to the third, how many centimeters to the third would be in a meter to the third? The answer is 1 million. Okay, so you want to convert centimeters to the third in the bottom to meters to the third. So you want to divide it by 1 million. So you're going to have 1/1,000,000th of a meter to the third. So that's going to be the part for your volume. So you want to go ahead and write that down and then put that on the bottom of your fraction, draw a line above it. And then the top part isn't so bad. So 3.337 grams, converting that to kilograms, you just divide by 1,000, which means you move the decimal place 3 places to the left. So it would be 0.003337 kilograms. You got to move 1, 2, 3 over here. So you're going to have 2 zeros here. So it would be 0.00. Oops, I'm having a hard time writing that. 0.003337 kilograms. Then divide that number, the 0.003337 by 1/1,000,000th, and that's going to give you the answer. Which, if I'm remembering correctly, I believe it's this one right here. So let's go to the next slide and look at it. So we wind up with 0.003337 kilograms and 1/1 millionth of a meter to the third, and the answer is indeed 3,337 kilograms. So the answer is E. Next slide. A combination of sand, salt, and water is an example of. All right, so think about this in your mind. If you mix salt in with water, can you see the difference after the salt is dissolved? No. So if they just asked for salt and water, that would be a homogeneous mixture. It wouldn't be a reaction, because when you add salt to water, what you get yourself is a solution. Nothing's reacting, and there's no chemical reaction. It's just dissolving. Same thing for the sand, but if you put the sand in, can you see it in there? Take the sand, put it in some water, and stir it up. What's going to happen? Well, you're going to see the sand particles, right? So you can see the water and you can see the sand. So that means you can see more than one phase in there. So that is a heterogeneous mixture. So the answer is A. Next. All right, so here, let's just try to write this out. Density is mass per volume. So what happened here? Density is mass per volume, and now we want the volume. So it turns out that if you rearrange this to get volume on one side by itself, so we're just going to rearrange this. Multiply both sides by the volume, divide both sides by the density, and the volume is going to be the mass over the density. So I would recommend, you don't have to do this, but I recommend that you do get familiar, like familiarize yourself with how to do this rearranging bit, because we're going to be doing it all the way through this semester and all the way through 1412. And then we know what these two things are, and they're actually in the right units. Can you believe that? So just substitute in here 1340 grams, but I'm not going to try to write that. So it's 13, but I would, if I were doing this on the board, I would, but it's just too tedious. So 1340 grams divided by the density, and it's in the right units. I can't believe it. So 2.67, and again, I'm not going to write the units, but the units would be grams per cc. So just take your calculator and divide that. And so I'm just going to do this like an approximate number in my head. It's going to be, let's see, 450 maybe, but it'll be more than that. So like, let's say 480 or 490. So, I mean, I don't think this is exactly right, but it's close. It's close, so just hold on, bear with me for a minute. Okay, and that's milliliters. And the reason it's milliliters is because we're dividing grams by grams per milliliter, or cc or whatever. We're dividing grams by grams, so the grams cancel. We have 1 over milliliters, which turns out to be milliliters. If you don't see that, just write it all out longhand. However, they don't want it in milliliters, they want it in liters. So there's 1,000 milliliters in a liter. So to convert this to liters, you can multiply by 1 over 1,000, or you can divide by 1,000, or you can just move the decimal back 3 places to the left. So it's about 0.5 liters. So we're looking for an answer that's about 0.5 liters, and it's not that one. That's not even close. This one looks right. This one's not even close. This one's not even close. This one's not even close. So I'm going to go with B. Let's go to the answer. And it is indeed B. So if you want to look at it further, here's the explanation. Next slide. Running out of time here. So I'm just going to read this one and give you the answer. Precision means how close it is to other measured numbers, E. So it doesn't mean it's accurate. As we said before, precision means that everything's hitting in the same spot, even if it's wrong. It doesn't mean it's good. It just means at least it's precise. So like in the context of like if you're in the Army like I was 11B, which is ground pounder infantry, straight leg infantry. And that's all we did was shoot M16s, clean them. And so when we went to the range, we were looking to get a group, what we used to call a good tight group. where all of the shots are like right on top of each other. And then what you can do is if you're not hitting the bullseye, you can just make an adjustment in your sight, in your windage or your elevation. And then you're still getting that good pattern. You're still precise, but now you've moved it up to the bullseye. Okay. Anyway, for the sake of time, let's move on. Next. Next. All right. An hour and a half. I've got to stop. So I'll see you in chapter 2.